2.3 is going to continue our discussion of sets. We're actually going to do set operations, and you kind of could classify Cartesian products as one of those set operations, and we will. The title separates it out, so I did as well. But we're going to do set operations in Cartesian products. The first set operation we're going to talk about is an intersection of sets. So an intersection of sets is the set of elements common to two or more sets. Most of the time we're going to deal with two. If our sets are, let's say, A and B, the intersection symbol is an upside down U, or horseshoe shape, that goes between them. So the key word here is the word common. Now, you have the phrase, or you know the word intersection in everyday language if I talk about the intersection of two streets, right? So we've got an intersection just right outside the window, Kickapoo and MacArthur, right? They cross right there. The intersection is actually the part where they cross. Okay? It's the part that the two streets share, what they have in common. And that's exactly what we mean by intersection here too, what something has in common. So if you're taking a look at the first example here, we've got a universal set. It's got some letters in it this time. The elements are A, B, C, D, E, F, and G. We've got a set X, which has A, C, E, and G. A set Y that has A, B, C. And there's a set Z that has B, C, D, E, and F. Okay? Again, this is one of the reasons why I don't want you to have to write all this down, is if you've printed the notes, you won't have to. So this symbol right here says, I want to know what the sets Y and Z have in common. Okay? So taking a look up there, this is a set, which means the answer is going to be inside of curly braces. Somebody tell me one item that they have in common. E? Yeah? Did I hear that? E? B? B? So I wrote it wrong, didn't I? You guys said, okay. B, and I wrote E. Okay, B, what else? C? What else? That's it. So the intersection is the sets B and C. It's what they have in common. All right. We also have what's called a union of sets. So a union of set is the set of all elements in either or both, / all if there's multiple ones, sets. Notationally, it looks like a U. All right, so you've probably heard the word union referred to in a marriage ceremony, in a wedding, right? The union and the two become one. So when you talk about a union, it means your kids are my kids now. This happens sometimes, right? Your car's now my car. Your house is now my house, and all the debt you owe, I now owe as well. That's what it means when they talk about a union. Everything I am and everything this person I'm marrying is gets pushed together and it's joined, both legally and hopefully spiritually and everything else as well, right? You get it all. It's a package deal. Take it all or nothing. Okay, that's a union. You get everything. And that's what it means in terms of sets as well. It means you get everything. Everything that's included in either one individually gets included in the union. So we've got the same sets that we had on the previous slide, right, described here, and the same sets described here, Z and Y. But the joining here is a U now. So I need to list everything in either set. So somebody tell me the first thing you want to list. A. Then what? B. C. D. And F. And notice we don't list anything twice. Right? Just because I'm married now doesn't mean that somehow that student loan doubled in size. We didn't get two of that thing again, right? We just got one loan per person maybe or whatever. But yeah, we don't list, in other words, the B and the C that they have in common twice. We just list it once. So this is the union. Everybody with me? Excellent. The next one is a difference of sets. So before I even describe, somebody tell me what the word difference means from algebra that you've seen before. Oh, I heard it. Somebody say it louder. Subtraction. It's very much the same idea here too. That was not written very well. Difference of sets, okay? This is the set of elements belonging to the first set and not to the secondary set. And the notation looks like subtraction. Whoops, we'll use the same A and B I used before. A minus B. Okay, so obviously it isn't exactly subtraction because I'm not actually subtracting numbers. I don't even have any numbers in this problem, right? There are no numbers listed anywhere. But what your image needs to be is your image needs to be taking the first set that's listed. In this case, it's X. So you take that first set X, and you list everything that's already in that list, except the items from that list that are in the other set. You remove those. So let's go back up to what those were. A. A is listed in set X right here, yeah? Is it listed in set Y? Yes, which means I do not list it now. I remove it. Okay, that's the subtraction idea. I'm sort of taking it out. I'm taking it out or removing it from the list. How about C? Take it out because it's listed in set Y as well. E? Nope, that one's okay. And G? That one's okay, so it gets left in the list. Now, I don't go adding the additional things from list Y that didn't get removed. So I don't go adding additional stuff. It's everything from the first set, which was A, C, E, G, and remove the stuff that was in the second set and only list those items now that were previously there. So this one would be E and G. And that's it. Say that again?
Would it be negative B along with that since you're taking the difference?
So it isn't subtraction, it's a removal. Okay? So we start with set X, and we remove everything from X that was in Y. And you're saying there's something in Y that didn't sort of match up between the two, and you're right, but that's not part of the difference of sets. It's only the stuff that's in the first set, remove the stuff that's in the second. And yes, there was something in the second set here that did not get removed, but it was never in the first set to start with, so it does not get included. Okay? So I want to give you a verbal description, and we'll see if I never write this one down. I always create it when I do it. So I have a brother-in-law, and my brother-in-law has a daughter from his first marriage, and that marriage is not still in existence. He's remarried since. And his wife now, he and his wife now have 2 children together, and then they have actually one on the way as well. Okay? So the daughter that he has from his first marriage is Madison, and then his children that he has now are Adam and Jocelyn. All right, so if they were to describe their family, we could talk about their family being these kinds of sets. Okay? So if we wanted to talk about, let's say that we have Adam's family as set A, capital set A for Adam, okay? Yes, he and his son have the same first name, so that's going to be, we're just going to try and avoid confusion in the classroom. We'll try. And then his wife's name's Jody, and so she's going to be set J. So if we talked about the intersection of the sets, that is the intersection, what family members they have in common, and we'll talk about bloodline in common here so that this will work, okay? In common, bloodline in common, the 2 family members that both share the DNA from Adam and Jody are the 2 kids they have together, plus the one on the way, right? That's the intersection here. We've got Adam and we've got Jocelyn, the Adam and Jocelyn that are the children. If we talk about the union, that is all of their children, plural, for everything, Madison gets included as well. Make sense? So then we get all three of them. We get Madison, we get Adam, and Jocelyn, all three of the children plus the one on the way. Doesn't have a name yet. Probably won't till it's born. That's the way things happen with them. Okay. The third item then is we could talk about the difference of sets. If we took Adam's children, which is all three of them, minus Jody's children, biological again as well, right, which is just the two that they share now, then the difference would be just Madison. Are you following with me? So we can talk about this in terms of a family as well, and it works pretty well. And I pick on their family just a little bit because it does the structure that I want it to here. Okay, so there's a great example for this structure. So this would be an idea of doing these three different operations of sets. All right, Cartesian product is the other component of this section. A Cartesian product has to do with ordered pairs. Where have you seen ordered pairs before? Graphing, right? Like algebra stuff, pre-algebra stuff, right? You remember seeing x comma y, and it talked about a location on a Cartesian plane, hence the word Cartesian here. All right, so an ordered pair is an ordered pair, A comma B, where A is in set A and B is in set B. We call A the first component and B is the second component. And in general, the point AB, that ordered pair, is not equal to the point that's the ordered pair BA. So jot that down first. So we got this idea of ordered pairs. And we're going to take this idea of ordered pairs and we're going to create all of the ordered pairs possible. And when we create all of those ordered pairs possible, we have what's called the Cartesian product. So if we take every set that's A and every set that's B, and we pair them up, and then we pair them up a second time, we pair them up a third time, we do all the pairings possible, that's the Cartesian product. So imagine something like this, right? There are, and we'll do this example in a minute with the numbers. There are 4 ladies and there are 3 men, and we want to figure out how many ways we could pair them up. Okay, dancing partners or something like that. Okay, well, we need to pick one person and put him with one other person over here. We could have taken that first initial woman and we could have put her with male number 2. Or we could have taken female number 1 and we could put him with male number 3. Right? We could do that pairing. And we could do the same thing with person number 2 and then person number 3 and female number 4. All of these, we could do these pairings. That's called a Cartesian product. And after we're doing a Cartesian product, we're going to do an actual example. This one's got letters, not females and males like I just created, but has the same idea. We have X, which is the items A, C, E, G. These should look familiar. We've used them now in 3 other examples. We've got Y, which has points or letters A, B, and C in them. Some of them have letters in common, and some of them don't, right? Like they're not completely in common, but they're also not completely separate. And that's okay. It doesn't affect anything. So what we want to do is we want to find an organized way of listing everything so we don't leave anything out. So the way that I handle that is I take the first point in the first set, and I'm using that set because that is the first set listed in my Cartesian product, X. And you see that there is an X between them, hence product, right, multiplication. So this X right here between them is indicating that this is a Cartesian product. So we're going to list a bunch of ordered pairs. We're going to start with the point A in set X, and we'll join it with the first coordinate or the first element in set Y, which is also element A. So we've got one ordered pair that's AA. I'm going to go ahead and take that same A from set X and join it with the next element in set Y, which is B. And then I'm going to take that same element A in set X and join it with the final element in set Y, which is C. And that is every way that we can write A first. So I don't have any more to write with this A. It's done. But I'm not done. I need to move on to B, right? Well, not B, to the second element, which is a C, actually. So I'm going to list C. C and what? A, because that's the first item from set Y. And then I can list C and B, and then I can list C and C. And I'm done with C. And I'm moving on to what letter? E. And I can list E and A, and then E and B, and then E and C. And I'm done with E. How about G, last one? G and A, G and B, going in order, Tyler, G and C. Now, these are listed inside of what kind of symbols? Parentheses, because this is an ordered pair, just like in algebra. You always put the ordered pairs in parentheses. But this is a collection of objects that form a set, and sets go inside of curly braces. So I need a curly brace around all of this. So I've got both symbols listed here, right? I will take off if your symbols are all screwed up. All right? Parentheses around each ordered pair, and then there are curly braces around the entire set. So this is a set of ordered pairs is what this is now. And you hope that neither set was too large, right? Okay. So let's take a look at one other kind of cool thing about this. We've talked about cardinal numbers in a couple of different contexts now. Actually, in both the last two lessons, we've talked about cardinal numbers. We're going to talk about it again. So if we have a Cartesian product where n of A and n of B are the number of items in A and B, right? We're familiar with that, right? Those are the number of items in those sets. Then if we want to find the number of items in the product, we multiply the number of items in set A times the number of items in set B. Now that doesn't give me the set, but it does give me the number of items in the set. So we're going to go back a slide to the one before. Just wait on the example for me below. Well, actually, the example below is the set before, I think. Yeah, it is. Okay. So this is the set we just did on the previous slide. Okay? Right? It was x cross y. It didn't have the n in front of it. We're finding something different here. But we're going to do this first from the formula. Okay? The formula above says that I should be able to take n of x and multiply that by n of y. Remember that n of here just means the number. So how many items are in set x? 4. How many items are in set y? 3. So how many items did they have total? Should be 12. Did we have 12 ordered pairs? Yes, we did. Now, if you're asked for the number of ordered pairs, I would highly recommend you not go and find the ordered pairs. That's going to take you longer, right? If you're asked for the ordered pairs, that is, you're asked the set, then you have to do this anyway. Right? And that's actually what we were asked on for, was to find this collection of elements, and we did. But on number 5, we're just asked to find how many of them there are. So if you're only asked for how many of them there are, you can use this shortcut formula. Good stuff, right? Yeah. All right. What we're going to do in this last box on this page, does everybody have sort of a, not maybe it's not, is it written as a box? Yeah, it is, a box on this page, is we're going to fill in all of the operations that we have seen with proper notation. Okay? So the first one we have seen was complement, and that was last time. So what does complement mean? Just in words first. What's the language? What is complement? Mason, you have an idea?
Opposite.
Opposite? We've described it kind of that way, right? The opposite?
So it's like everything that one has that the other doesn't?
Right, that's the idea. Okay, so the complement is the things that sort of are not included in one or the other. So if we're talking about the complement of A, the notation that we used last time looked like this. All right. So the first thing you'll notice is that we have x such that. So far, so good? And the description, this one that we even had on the board right here that Matthew had asked about, we talked about it in this sense. The first issue is that we have to have the item be in the universal set. So I wouldn't have done this particular problem that we did on the board here and talked about this item down here having the number 12 in it, because 12 wasn't in the universal set to start with. Okay, so it's got to be something that was from the universal set. And then it needs to be the opposite, like Mason said. So it should not be in, that is, it is not an element of set A. So it's all items in the universal set that are not in set A. And as we're doing this, because we're going to need this idea in a minute, I want to show you what a Venn diagram for this picture would look like. We did this before, but let me remind you for this particular one. If you have a Venn diagram, you've got a rectangle, that's set U, right? And then if you've got set A, that's a circle inside. And then A complement is where? It's just the part that's on the outside. So in terms of a picture, I'm going to shade it in. Everything that I've drawn here in yellow is A complement. The universal set includes the circle, but the A complement would not be inside the circle. Intersection. I haven't shown you symbols for this yet, so this is something that's a little new. We've got A intersect B. That you've seen symbols for. And this is the set of all X. Okay. What has to be true for something to be in the intersection? It has to be in both. It has to be common to both sets. So we've got symbols for that. We know how to write A as an element of A. I'm sorry, X is an element of A. And we need the word and because we said it has to be in both. And X is an element of B. Okay, and that and here means both. So let's try a picture of this one. All right, so what I'm going to draw is I'm going to draw two circles that overlap. One circle is set A, one circle is set B, and U is the universal set on the outside. Location-wise, where is the intersection? The part where they meet, right? The sort of, I don't know, football-shaped one in the middle, right? This piece right here in yellow is A intersect B. So the intersection is the overlap, where they cross in the middle. That's what we mean when we talk about the intersection of streets, yeah? So, all right, the next one we encountered today as well was union. So our symbol was A, there was a U, and then B. And we have the set of all X such that. They all start the same way, right? What has to be true for this one? No. What do you mean by outside, Marquez? Outside of the two circles or in the outside part of the circles? There you go, the outside part of the circles, right. Okay, so we're going to have some overlapping circles. Let me do the picture first since that's how you guys are sort of thinking about this, which is great. All right, so you've got a circle and they overlap. And the outside parts of the circle get included. Does the inside part get included as well?
No.
Yes, it does. Go back to the description. I'll label my circles. I didn't do that yet. Here's A, here's B. The description for union, we're back a few slides. It's here. What did it say? Yeah, either or both. Okay. So a union means we include everybody. My example of my family, right? My brother-in-law's family, it was everybody. Both Madison, the older daughter, and then the two younger children they share is all of their children. You get it all. Okay? So you get both pieces of the puzzle when you do that. So we need to figure out how we can write that in set notation. So what do I need to write? So we start out with something.
X is an element of.
I thought for a moment we're going to stop there at x. Yes. X is an element of one of them.
True.
Okay? So if x is in A, it's in the union. Okay? So I get married, I have a debt, it now becomes our debt. What's next? Or what do I write next?
And
We're going to write the word or. And this word or is not an exclusive or. It doesn't mean mine or yours, and it doesn't mean anything we have in common. It's an inclusive or. So this or means or, like either or both. That's what this word or means. Okay? We just put or. It includes both. This is one of those unfortunate things about English is that our word for or actually means different things in different circumstances. We're just running into that here. The word or that's being used here is the inclusive or. So it means everything in either or both. What needs to be listed next?
What is it?
Is an element of.
It's an element of B.
Right. And then the end. All right, so the only difference between its intersection and unions set notation is what? Or an and. It's the only difference in that description. So write yourself some kind of an important note, red flag, something that helps you to remember which one's which. All right, so or goes with unions and goes with intersections. All right, we're going to do difference next. A minus B. And we're going to have to start with X such that. And actually, I think it might help for us to do the picture first, just like we did last time. So I had two overlapping circles. Here's A and here's B. Okay, so let's remember what difference was. Difference meant take everything in set A, and then what do we do?
take out things that are in B.
You take out or you subtract or remove the things that are in B. What part of this picture is that? Just A on the outside, right, Matthew? So it's this part of A. So this kind of goes back to what you were saying, Marquez, of sort of just the outside of the circle. So you get just the outside of the circle when you do difference. And that's why, Mason, that we don't include that extra letter is because we're just removing the piece that was actually overlapping and not introducing any extra pieces. Okay? So in terms of my notation, what am I going to list next? X is an element of A. We don't need minus. And what? X is not an element of B. That gets us the minus, right? This says everything that's in A, which would be this whole circle. And then it says, but not in B, which means remove the part where it was overlapping. So we get this picture. Are we good with that? Okay. Cartesian product is not got a picture. But we do have a symbol, or a set of symbols we can use. So this is A cross B. What kind of elements were in A cross B? Ordered pairs. So I can't list them X such that, because they weren't elements X. They were ordered pairs, right? Now you can use whatever ordered pairs you like. I kind of like A and B here, so I'm going to use A and B. But you could use X and Y or something else if that suits your fancy. And then you're going to put the line. So this is telling you this is a set of ordered pairs. But we need to figure out what in the world this little a and this little b have to do with big sets A and B? So somebody tell me. Where does that little a have to do with?
It's an element of the big A.
Right, it's an element of the big A, right? The first coordinate is supposed to be an element of the first set. So however you've got it listed, whatever you listed as your first element needs to be an element of the first set. So if you'd listed X first, X would be an element of big A. Okay? And then the same thing would be true about the little b, right? Except that it would be an element of set B.
B.
Big B, yes. And then we're done. Okay, so it's a set of ordered pairs where the first element comes from the first set, the second element comes from the second set. We're going to do one more example today, and you guys might get out just a touch early, okay? Are you going to complain at me if I do that? Absolutely. Just to get your money's worth at all. You can hang out and talk with me if you want your money's worth afterwards. All right, we're going to do Venn diagrams. The last 3 problems in this set we're going to do Venn diagrams for. So we will do this one problem. We'll do the next 2 next time, and we will start into 2.4, okay? So we'll do group work next time, which means I would not ask you to turn in any homework quiz over this section because we're not finished with it. Make sense? Okay? But you probably should go ahead and get started working on it since it's still fresh in your mind. Are we good with that? All right. And you can start the My Math Lab too if you'd like. All right. I'm going to show you how I want you to do these problems. And there are other ways to do the problems. So I want you to be aware of that. If you have seen Venn diagrams before and have worked with them before, this may not be what you're used to seeing, and I'm okay with that, but I still want you to do it the way I'm asking you to do it. Okay? All right, this says use Venn diagrams to shade each set. So we kind of did a little bit of the shading on the last 2 slides where I drew the pictures and showed you what things look like when they intersect or do unions or differences or whatever. This one wants a union, but it doesn't want a union of A and B. It wants a union of a complement and B. This one's straightforward enough that we could probably reason our way through it without what I'm about to start with, okay? But if you'll notice on problem number 6, what happens very quickly?
It's not the same.
Does this look different than yours?
Yes.
Yeah. We have A complement, union of B.
Okay, we'll fix it. I'll fix it in a minute here, but somebody look at this for a minute, whether it's yours you're looking at or here. What happens?
It's listed. I mean, well, it's in parentheses.
Okay, let me ask that. It's in parentheses because how many sets are here? 3. I have 3 sets here, right? Can you imagine what it looks like to draw a picture where the 3 sets overlap? Starts to look like the Olympic rings, right? But just with 3 of them instead of 5. Okay? That becomes a lot more complicated, So what I'm going to show you over here is not crucial to here, but it's crucial to moving on from here. Are you with me? Okay. What we're going to do is we're going to list the first one is A and the second one is B and the U on the outside. Item number 1. Item number 2, we are going to list the areas with numbers. So we're going to identify them sort of by a number. So we've got area number 1, area number 2, area number 3, and area number 4. If you'll match my areas, then we'll have the same picture when we're done with the numbers. If you don't, it's okay. You'll still have the same picture. Your numbers will be different. Okay, so we've got a number in each of the different spaces. Everybody with me? Okay. What this says on top then that we're supposed to do is supposed to find a complement. So looking at the numbers 1, 2, 3, and 4, which of those numbers form a complement? 3 and 4. Remember, complement means it's not in A. And that's 3 and 4.
Does that mean?
Okay? You can put curly braces if you'd like. We don't need curly braces right here because we're just identifying spaces or regions that we put the numbers in. They're not really elements.
Oh,
Yeah. Let's do set B. What numbers are in the areas for set B? 2 and 3. And then what we're going to do is sort of like what we would do with, like addition when we were in 1st and 2nd grade. We're going to draw a line and we're going to combine them. And we're going to combine them with whatever operation we were told. In this case, the operation was union. What does union mean? Everything. Either or both, right? Everything. So everything that's in set A complement and everything that's in set B all get listed. So somebody tell me what is in the union of these numbers. 2, 3, and 4. You have to show me that work. If you get the right answer and you don't show me this work, you're losing major points. Major points. Okay? So you have to show me this work. But if you stop right here, you still have not done what the directions said, because what did the directions say to do? Shade. So take your pencil and we're going to shade. I'm going to change my color here. Something lighter. Let's try that. So I need to shade the region 2. I need to shade the region 3. And I need to shade the region 4, which is the outer rectangle on this one. So the only thing that didn't get shaded was region 1, which was inside of the outer part of A. So no matter where you put your numbers don't have to match up to mine. You're still going to get the same shading if you've done the problem correctly. So here's the danger maybe in this. I can't have the computer force you to do numbers when you do this on my math lab, okay? So please make sure that when you're practicing with this idea, because I am going to make you do numbers when you turn things in, either with homework quizzes or your exam. I want to see this work over here, okay? All right.